Now, I'm going to talk about, oh, sorry, I'm very pleased to be here. and to see Maarten sitting there. I remembered using to, that's not quite right, is it? Anyway, we used to sit on a bench with wall, I remember, several times. So this feel like home. Right. You saying something? Right, here I go. Now, I'm going to talk about the intergalactic medium. My name's there, but it's with WAL. And it still is with WAL. We've just submitted a paper, basically. It's quite an interesting thing to talk about. The intergalactic medium is many things. And nobody saw that. Okay. Right. We know that the universe evolved. And it's started and got to here. A bit of a mess to begin with. It sort of got some order later. And some people think, I know one particular one, that the universe came from an egg that hatched. And that's the egg. And it evolved from obviously being very dense and hot and all of this. It became neutral and recombined, that meant. It then reionized. So it went through recombination, reionization, and maybe resignation at the end. And it gained structure, and you can see some of it deep into space, Hubble telescope, and so on. So we know quite a lot about it, and there's other details, which I won't go into. And so I get to the quasars. Now, why the quasars? Well, because a quasar at some distance allows you to look through the universe and get spectra like this. One, for example, sees what we sometimes call the Lyman alpha forest, or the Lyman forest, because it's not just the alpha line. And so one can see gas, and you also see that it evolves. This is the famous 3C273. That's the hydrogen region. And this is another galaxy, quasar, and a higher redshift, and you see a lot more of it. And at the same time, one can see galaxies in the universe. So, for example, there's the quasar. Here's some galaxy gas, which produces a denser hydrogen line, but also metal lines. This is another example of that. There's the hydrogen lines, and here metal lines. So QSO absorption lines is, that's correct, a unique tool for studying the high redshift universe in the reionization, post-reionization eras. So what is the reionization era? You may recognize this. George is sitting in the front here. And it's this sort of region. And the point is, universe recombined, then stars came and reionized. And then galaxies like we see. And the process of cosmic reionization is a pretty important problem. You know, how does it actually happen? It started at about redshift of 1,000, and Gallen-Peterson's results show you that it changes markedly and maybe was fully reionized by about redshift 6. You might argue about the 6. And but with the rapid decline of the abundance of QSOs at redshift greater than 3 or so, the quasars themselves cannot have done it. So the idea is that star-forming galaxies have been seen as the likely agents, and knowledge of the redshift-dependent properties is therefore a central issue for understanding how hydrogen and helium became reionized. Actually, the helium won't have been reionized by the galaxies, that's the quasars. And that came later. It's delayed. Why do we have the lights on? Okay, so Gallen-Peterson trough, at redshift nearly 6, as you can see, and as George has shown, it changes with redshift and is a very good indicator. Now, coupled with that is the interstellar media of galaxies. They also have a crucial role here because they're intermediary. Stars forming within them replenish the interstellar medium with matter and energy, but then the interstellar medium fills interstellar space and blends in to the intergalactic medium, but let's call it circumgalactic mainly, and stars therefore are fundamental in the process of feeding back matter and ionizing radiation. So, in a bit of a summary, I mean not at the end yet, QSO absorption line spectroscopy coupled with increasingly sophisticated numerical simulations have revolutionized the view of intergalactic medium. And the beauty of this approach is that galaxies which you detect through this are detected independently of their luminosity because you're looking at them through absorption spectroscopy. And it would not be possible to see them in that very clear way otherwise. And we know that most of the intergalactic medium has been already enriched by stars not quite recently. So at redshift 3, about 90% of the baryons in the universe are actually in the intergalactic medium. So here are some new, well, not new, there's some data. Here is some data. Here are some data. And this is one of 9 spectra. And you can see absorption lines here. That's where the Lyman forest comes, and these are metal lines. So that's another one. Here's number 3, 4, 5, 6, 7, 8, 9. And that go to quite a high redshift, and each of them has these things. And these absorption lines we've traced through many ions. Carbon 4, silicon 4, carbon 2, silicon 2, and nitrogen 5. And here's hydrogen at the bottom on a different scale. And you can see the structure. This is called a system, and within it are components. This is a simple one. Here's another one in one of the objects. And this is the simple one I just pointed out. And within each system, one can see components which track through the other ions. So, for example, here's carbon 2, which is low ionization, here's nitrogen 5, which is high. They both appear in carbon 4. And to some degree in the others, but weakly. Nevertheless, they are part of the same entity. So what we're looking at is single-phase ionization entities, which make up a system, group of such things, and nevertheless, you can track through in a single sight line through several of these, which relate physically to each other. That's very important. Here's a more complex one I won't go into detail, but for example, carbon 4, carbon 2, the sort of narrow ones are there. They're sort of separated. And you see them in the carbon 2 as well. They all track through, while carbon 4 has some broad ones as well, which you don't see so much in the low ionization case, but they're still incipiently there. And if one tracks this through redshift, you find there's no evolution. Now, this is all the carbon 4 systems. This is the simpler ones. These are the more complex ones. And these are the summed systems. These are components at the top, and these are the summed systems. And it doesn't change with redshift up to about 4.5. That's interesting. This is the evidence, if you like, the more proof. This is non-evolving through the dotted line, and the data go through it. You can do this for the other ions. It's mostly the same for silicon 4, but the carbon 2 and silicon 2 and nitrogen 5, of which there's less, sort of fewer components one can detect because they depend on the where they reside in the spectrum and how close they get to the Lyman lines and so on. So there's fewer of these, but nevertheless they do seem to actually evolve. Furthermore, the clustering. This is clustering of components, carbon. And I won't go, these are details, let's say, but generally you can see it goes as one might expect for a sort of, this is a two-point correlation function, and one gets, you know, a combination of things which give you this sort of profile up to a few hundred kilometers per second. But if you treat these are components, as said, if you treat them as systems, then you find no clustering whatsoever. In other words, the systems don't cluster, but the components do. Well, that tells you something. It's that the components are part of entities, the systems, and the systems themselves aren't sampled very well because you've got a single site line. So supposing one says this is all due to galaxies, if you go through a cluster, you might hit one galaxy, but not others, if you look at just the system. But because you're seeing this clustering, what you're seeing when you hit a galaxy is a complex combination of regions near the galaxy. And the issue, I'll raise that, I'll bring that back. But if one now takes not just simply the ions, but the ratios of ions, you also find silicon-4 to carbon-4, that does not evolve. Had it had a step somewhere, as some have claimed, around redshift 3, one might say, well, there's a difference because helium-2 is ionizing rather late, and that will be an indicator. But you don't see that. Turns out it's not a very sensitive indicator of that. And here's the other elements. To some extent, they do evolve, but really not all of them do. It's generally unevolving with some evolution. But one should say that these ratios, carbon-2 to carbon-4, silicon-2 to silicon-4, silicon-4 to carbon-4, etc., are not complete indicators of the ionization state. So what we'll look at in a minute is combinations of those. But what are we doing looking at them in the first place? Well, we're seeing how they're ionized. Galaxies must be there. Here's a galaxy in the sort of, let's say, non-ionizing region. Somebody observed. I mean, that has been observed. Many people do it. Chuck does it, of course. In the Lyman continuum, you see nothing. In other words, the ionizing radiation hasn't got out. Now, that is a big thing here. The ionizing radiation begins at 912 angstroms for hydrogen, and you'd expect a drop, but it depends on what is in the way. Now, if hydrogen is in the way, you don't need much hydrogen to stop it. About a few 10 to the 18 per square centimeter column. You have much more than that in a galaxy. And there's dust there and various things. I don't need to go to detail here. There's also the intergalactic medium that still has some hydrogen that is in the way, and in the sight line to that galaxy also will do some absorbing. So there's several issues about the escape of ionizing radiation that you have to take care of. It is claimed and measured that this rises with redshift, and that at low redshift it's 0. What we saw a moment ago was a redshift 1 galaxy, and around there you don't see any, but it becomes more, the escape fraction increases with redshift. Sorry. So we should look at the whole thing and see what the radiation does when it reaches the absorbers that I've already shown you. Haardt and Madau have, for a long time, done this work, radiative transfer in a CLUMPY universe, to give the ionizing background that one would expect from quasars and galaxies. And one has combinations here that take account of physics involved, clumping factors as well, good treatment of photonization, and question to the issue of galaxy emissivity, which includes star formation history as well as escape fractions. So this is what one finds for the star formation history, and here is the quasar luminosity, and this is galaxy luminosity. So you can see the quasar luminosity drops off very rapidly. Well, there is one quasar seen at redshift 7 roughly, as we heard, and it peaks around 3-ish, drops again, whereas galaxies come in later and take over, and this is the combination. So if you take that ionizing radiation as it stands, at low redshift, redshift 0, you can match observations quite well with the output of those computations of Haardt and Madau. Now, if one then looks at what the outcome is, and don't be scared, this is not complicated. What this is different redshift bands, 1.9 to 2. Is it 6? Can't see it properly. 2.6 to 3.4, 3.4 to 4.4. So this is one redshift band, and this is just quasars. This is quasars, which are still blue there, and the galaxies included in the red. And this is including some sort of contrived effect of helium-2 reionization. I say contrived because the Haardt and Madau results don't include discrete sources. It's volume ionization. You have to take account also of the fact that alpha elements give a sort of band of values and so on in working out, so does nitrogen. So if you look at the data now that compares just the quasars illuminating, that just gives the quasars illuminating the absorbers, the results you get are this between these two bands, and that's due to the alpha element range, 0.4 or so. And you see it doesn't fit the data at high redshift, but at low redshift it isn't bad. And this is for silicon 4 over carbon 4, nitrogen 5 over carbon 4. And when you go to silicon 2 over silicon 4, and each one, by the way, I should say, is on an abscissa of carbon 2 over carbon 4, which relates quite closely to gas density. If you look at that one, there's no change with redshift in the data, sorry, in the computation, but there is in the data, drops. It's not too bad for the silicon 2 over carbon 2. So the data so far shows, back again, it doesn't work very well with just quasars. If you take the galaxy case, the red one, it works better for silicon 4 over carbon 4 at higher redshift. It's okay down here. It's partly here because of the escape fraction is much higher from galaxies here, and the galaxy component is less, and so you have the quasar, the galaxy is more dominant, and this is how the improvement comes about. But it doesn't work for silicon 2 over silicon 4 or the other. So this doesn't work. If you add the bit of helium-2 reionization, it helps a bit, particularly here, but it doesn't work because, once again, this doesn't fit. So you need to put something in for galaxies. Well, the galaxies are local to these absorbers. If you take them, as I've already said, they are clumped around. We've seen the statistics of this in terms of clustering, and there's other evidence, which is very direct. This is a galaxy spectrum. You see, by the way, P Cygni profiles, and this is the observed non-ionizing emission from the galaxies. This is in the ionizing region. Sorry, I beg your pardon. This is in the Lyman region and a Lyman alpha sort of region. And intergalactically, there would be some drop here, some decrement. You can still see it, but the ionizing region extends from here. Stardell and others found that at large impact parameters around galaxies, this is the impact parameter, you can see those same elements. Silicon 2, carbon 4, carbon 2, out to these quite high distances. And therefore, and this, by the way, is a simulation by Shen and others, which shows what might happen in a simulation. Of course, you can't always believe simulations, but you've got to expect to get some of the gas out, let the light out. So techniques have been proposed where quasars, sorry, I beg your pardon, supernovae have produced sort of channels to allow the light to escape out of the galaxy. You saw that at low redshift you got nothing out in the ionizing region, but if at a higher redshift you got channels. Canadians found that you could find sort of sloshing modes in the hydrogen where stars appeared and therefore would let the light out. So you might say that's how the radiating component gets out. And we're only talking about this bit between 13.6 eV and 50 odd, where helium-2 has its edge. And dust doesn't make any difference. You might think it would, but it doesn't, because of the ratios between the effect, comparable effects, much higher effects with hydrogen absorption. So if you take the spectrum like this from a nearby, as shown by Steidel, galaxy, and there's two distances, 20 kiloparsecs and 80 kiloparsecs, then this is the component you get on top of the background, which would be this. So here's the result for just a high redshift case in this case, and it doesn't work. The galaxy light doesn't do it, doesn't fit the ratios. And if you look at the silicon 2 over silicon 4, it's even worse because it goes in the other direction. It's bad for this one as well. So you can't say that the light that gets out from what you can see to be the full spectrum that you expect from a galaxy having a full saltpeter IMF and everything else, the stars are observed in the non-ionizing region, it doesn't work. So is it that we've not got photonization, but we've got collisionalization? No, it isn't, because that would be collisional, and our results are all along these things. So we've got the right sort of ionization. Is it due to parameters, due to, like, for example, metallicity in the absorbers or higher column density in the absorbers? The answer is no. Here, just take this one case, silicon 2 over silicon 4, varying quite strongly in those parameters. It doesn't change anything enough. So how do we do it? Well, the answer is runaway stars. This is where I have to finish. Runaway stars do it. I perhaps have 3 minutes. Runaway stars get out of the galaxy because of dynamical effects or supernova effects, but actually dynamical effects are dominant. This was learnt before, but here we go. So, by the way, this is not runaway stars. Those are Perseid meters, but it's sort of it's the sort of thing you might expect. And Crunroy and Crater did try this, and they found that they could be dominant. But what they didn't do is use the spectra. Stars have different lifetimes. I'm not telling you anything new. If you take the main sequence life, if you take the mass, main sequence lifetime goes like this, and it seems to flatten around a few million years. And if you take escape times from the galaxy of those stars which have been ejected, they leave their source, their place where they've been evolved, where they've been produced, and they get to maybe 40 kilometers per second. They have to get out the hydrogen. So it's a few hundred parsecs. Different times given to allow them to do this, you find quickly that you lose the hottest star for just a few mega years. And that's been the problem. The hottest stars are the ones that give you the wrong data when you compare the ratios of these elements with the computations that you get. And the idea of using runaway stars with certain lifetimes before they can get out, and those that survive are the lower mass stars, not the high ones. They're dead before they get to the boundary, but the lower mass stars do, and then you get a helium-1 drop. There's helium-2. That helium-1 drop makes all the difference. Here's that. This is the old full spectrum case, but this is the runaway star case, where the ones that are left have the collective spectrum that give you this. This is what you get for silicon-2 over silicon. It evolves properly. This allows, these are a lot of high sort of upper limits, and this is correct. And if you take a bit more sort of, modify something to see how you might have the sensitivity of this, for example, the abundance of the metallicity of the absorbers, it doesn't change it much. Now, this is the silicon 2 over silicon 4, and there's a result now, and it fits. These, remember, are two results. One is 20 kiloparsecs, and this is 80 kiloparsecs, and this band is right. It also fits very nicely here. And again, if you put a bit of extra metallicity in, it works. So that's the end, where hydrogen absorption systems evolve strongly. Several bulk properties of the metal absorbers are almost invariant over the whole redshift range observed. The absorber components exhibit strong short-range clustering, but no clustering on any scale between composite systems. Therefore, the strong absorbers reside entirely in the circumgalactic regions. And remember, we're talking about the IGM. At redshift lower than 2.7, the radiatively transferred cosmic ultraviolet background due to QSOs does dominate and everything works. Extending to earlier times, the radiative contribution from galaxies in the largely unobserved region 1 to 4 Rydbergs becomes strongly dominant. But the ionization structure of comet elements yields, while it yields crucial information on the origin and spectral makeup of the evolving ultraviolet environment, you have to bring in the naturally modified radiation from the preferential escape by lower mass runaway stars from galaxies local to the QSO to get the observed results. And that must be, therefore, how the universe was ionized from the beginning. Thank you.
Time for 1 or 2 questions. Matt?
Are you just saying that at the higher redshifts you would like the ionizing light, radiating those quasar absorption clouds, to have a good helium-1 edge in it? And
A good yield at...
a good helium-1 edge is what you want. And
You do need a good helium-1 edge, yeah.
Okay, so why can't you just get a more realistic model for the stars in the young galaxies there? Don't have them all be continuous at star point.
Well, you showed me one result where you cannot conclude that because you see the whole band of masses up to, let's say, 100 solar masses. In every case one sees P Cygni profiles, you see hot O and B stars there. You see the hot stars. In the non-ionizing region, you see those spectra, but you can't see it in the ionizing region, and you can only infer it from this. Now, if you try, for example, bursts or instantaneous bursts, of course you can wait a few mega years and you get the result. But that's not good statistics. That's not like the universe. It might be like that in certain cases. We see this on aggregate for everything. So it really has to be that. And Chuck, I think, will tell you that.
Juno?
So it's interesting that you need these low mass stars to preferentially get to moderate distances.
Low mass being 20 solar masses or so.
Okay, so the idea there is that you're just getting supernova kicks. So do you actually have an idea of what the velocity distribution you need to get the right number of 20 solar mass stars out to the right distances? So is this just coming from asymmetric binary evolution where you have supernova kicking?
Binary or triple or whatever.
Well, that's what I'm asking.
Yes, yes. Yes. Basically, you just need a few percent. And that is what the escape fraction is. And I didn't say it, but the escape fraction is generally worked on in these things, and it seems to be close, is the right amount that will reionize the universe. And so it's of the same order. And also the distances in the galaxies, which are smaller at high redshift, you don't have to travel so far, and so on, all work out. But I'm not saying it is exactly right, but it doesn't seem to be sensitive to the parameters very much. It's not finely tuned. But it certainly does not work if you have the full galactic spectrum.
We should move on, so let's thank Alec again.